4, part 2. I actually didn't intend to break this into 2 parts, but I made a mistake in Excel, and it was kind of a pain, and then the video was getting long anyway, so. Alright, so 10.62, standard deviation. In chapter 4, you learned about residuals, the distance that points are from the line of best fit. In the process of determining the LSRL, you had to square the values of the residuals to make them positive because the distances are usually positive. You learn that statisticians prefer to make numbers positive by squaring them instead of by using absolute value. So obviously, we use absolute value up here and mean absolute deviation. So we're not going to use absolute value again to do standard deviation. We're going to square it. I think what you'll notice is these two things are very similar. They have a lot in common. However, here we're using the absolute value. Here we're using squares and then square rooting it back. So anyway, that's kind of a little thought about that. The standard deviation is yet another measure of how much variability or spread there is in a data set. And again, the standard deviation is going to use the mean. So we would not use this if we had outliers or a skew left or right or a tail left or right. We would only use this if we felt like our data was normally distributed or normally distributed or something along those lines. So I want to kind of write down a list of sort of what the order is. So standard deviation is the average of all distances to the mean after the distances have been made positive by squaring. After calculating the average of the squared distances, take the square root till the units come out correctly. Okay. So here's really what we're going to do. One is we're going to calculate our misses. Once we've done that, we are going to square those misses. You might want to kind of jot this down on the side because you will be expected to be able to do this. 3, we want the average of the squared misses. And then we're going to take the square root of step 3. Or the square root of the average of the squared misses. So that's what we're going to do. And again, I'm going to use Excel to do this, but hopefully this time I do not screw it up. I didn't mean to add that to my favorites, but whatever. I'll go back and change that later, I guess. So when we look here, we said that we were going to start by calculating the misses. And I know we've already done this before, but we're going to say that this, and this is where I screwed up last time. I actually clicked this cell, which is bad news, and then when I copied it down, I didn't realize that it had made a mistake. So there's all of my misses. And again, what I want to do is I want to square these misses. So I'm just going to write a formula. And again, you're supposed to be doing this by hand, where I take this number and I square it. And again, if we go to this symbol right here, that caret, that means exponent. I'm going to go to the second power, hit enter. So I'm going to bring this down, and I have all of these squares. The third step I'm going to do is I'm going to get the average of these squares. So again, I can just go here and type equal average. I want the mean, but again, the software here considers it the average, not the mean, is the formula we're going to use. So I have the average of the squared misses. So again, I have my miss, I squared my miss, I took the average of that, and now I just want to take the square root of that. And you will see I get 10.85. So this is my standard deviation. Again, that's how it wouldn't surprise, the middle's 40. It wouldn't surprise me to go 10.8 in one direction and 10.8 in another direction. Most of the data should fall within 30 to 50. And if we go here, we can see between 30 and 50, almost all the data falls one standard deviation plus, one standard deviation minus. Again, if you look at that as like 10 or 11, add, let's call it 11, add 11 to that and subtract 11 from that, you get 29 and 51. So that's where most of the data should fall. Over here, we get something a little bit different. So we are going to write a formula that subtracts from the mean of 40. Again, we'll copy that along. Again, we will square our misses. So here's a miss, and I'm going to square it. So I have all this data. All these things are squared. Again, I'm going to take the mean or the average of these. Again, you should grab all these up and divide to get your average. And then finally, I want to get the square root of this number. And I get 18.8. And again, I would not be surprised to see a spread of, let's call this 19. 40 minus 19 is 21. 40 plus 19 is 59. So between 21 and 59 should be the bulk of those numbers. And you can see that they are. But you can see how much more spread out this one is than this one. If we applied this deviation to this data, you know, and we can only go 11, we would say between 29 and 51. You can see we capture a lot less of it, right? Here we capture this much of it, but with this deviation, we can actually get a couple other numbers here and a couple other numbers here. It widens a bit. Obviously, some stuff falls out of the standard deviation, and we'll talk about that. I think in the worksheet video, I'm going to make a worksheet video for this as well. All right, so jumping along. So without using your graphing calculator, find the standard deviation of each sugar in 1060 and compare the variabilities of the two sugars. Again, we said that sugar W has a standard deviation of, was it 10.86? And we said that sugar P has a standard deviation of 18 point, I think it was 87 or something like that. So again, we still see more spread in P, and again, if we look at that, that's not a surprise because we can see that spread here for sure. We see that the green one has a more spread out than the red one does. Alrighty, so back to, we will see if I can open up this one. It worked. It's so weird how sometimes it works and sometimes it doesn't. All right, so 1063, it says calculate the standard deviation of your team's tosses from the 40 holes of golf event. Compare your result with the other teams. Well, we can't compare our results with the other team, but we can go here and we can calculate the standard deviation. If you'll recall, this was the data that we were asked to use. There's 5, 10, 15, 20, 25, 30, 35, 40 pieces of data. So we want to calculate the standard deviation of that, and I went ahead and I pre-slugged this information. So you'll notice it shows up in 2 rows. So I'm going to have to kind of add those together, but I need to have the mean. I need to have the sum. Do I need the sum? I can't remember. Anyways, let's get the average of these. Let's get the mean. So I'm going to say equal average, and I'm going to use the control key to sort of jump to the next column. Am I missing something here? Oh, I see it did it over there. I wasn't really noticing that. Okay. I expected it to highlight them all at the same time, and it didn't, so... Alright, so I'll go here, and then I'll go here, and you can see I have C 3 to 22 and G 3 to G22. I kind of expected to see that purple box remain, and it didn't, so it kind of confused me. So I have my mean. My average is 73.525. So what I'm going to do is I'm going to calculate my misses here. I'm going to say, alright, well, this thing minus 73.525. This is my miss. Again, I will bring that down. Just so I don't have any issues, I'm going to rewrite the formula over here. So this one minus 73.525. And again, just to make it clear if it's not, all I'm doing is subtracting 73.525 from 2. And just so I don't have to keep doing that over and over and over, I'm writing a formula that does this all for me. Now what I'm going to do is square this number. So I'm going to write a formula that says, all right, take whatever's in this box and square it. And again, now I'm copying this formula down. This isn't really about how to use a spreadsheet, but this is just what I'm doing. So you can see on this one, it changes the formula. It goes from D to D4 to D5 to D6. So it's just taking the next one and multiplying it. So again, same thing here. I'm going to take this number and I am going to square it. And I will copy that down. All right, so that's step 2. I've calculated my misses and I've squared my misses. Now what I want to do is I want to get the average of those misses. So I'm going to go here and I want to get the average of the misses. And that is going to be equal average. And again, I'm going to use the control key to get this data. So you can see that's the average of my misses, and now I want the standard deviation of the average of misses. So I want the standard deviation and I'm going to put P here because I want the standard deviation of the entire population, and we can talk about that kind of more later. Equal standard deviation. Oh wait, no. I'm sorry, my mistake. I'm confusing something right now. I apologize. I want the square root. I'm jumping ahead to another problem. I'm sorry. So I want the square root of that. So you can see the square root of this. Again, should be the square root. Darn it! I apologize. I got a little ahead of myself. The square root of the average of the misses equals this. So this is the standard deviation of this data. Okay, so I calculated the misses, then I squared those misses, then I took the average of the misses, and then I took the square root of those misses. So again, ignore what I said about the standard deviation of the population. That will come up later. Shoot. All right, so anyway, 1064 says the standard deviation was probably not appropriate way to find the spread of your team's golf data. Why or why not? Well, if you'll remember the golf data, and we keep talking about this, right? The golf data looks something like this. So what happened was we had a tail to the right or a skew to the right, and then we had some outliers. Well, we wouldn't want to use the mean with this because remember, the mean is only used for like standard distribution or a normal distribution. So we wouldn't want to use the mean with this, and the standard deviation comes from the mean. So we would say, that's not good to use. Instead, what we should use is we should use the median, which is the interquartile range, because we have kind of funky data with the tail and with outliers. So that would be the logic behind that. All right, now let's go to 1065, and this is where I was screwing up on the last one, and I apologize for that. But it says your teacher will now demonstrate how to determine the standard deviation using your calculator. Well, we used 3 calculators so far. We used Excel, we used the TI-84, and we used Desmos. So we had a lot of different things going on here. So I'm going to show you how to use it with each of them. But first, I want to talk super briefly about different standard deviations. So one is if you have the entire population, which we do, this is everything in the world, we're more certain. Remember, because standard deviation talks about like how much things can deviate from the mean or the middle or the average. So if I know all the data in the entire population, I have more certainty than if I don't know. So imagine like polling, right? The last election we had for president, well, at least as of making this video, the last election we had for president was Trump against Hillary Clinton. And all the polls showed that Hillary Clinton was going to win because they didn't ask everybody, right? They sort of took it like this. They had this, here's the entire population, and they asked this many people, hey, who's going to win president? And then when they got the answer, they went ahead and said, well, that's what everybody thinks. And what we know that they ended up being wrong on that. That wasn't the case. So there was less certainty. So they would use normal standard deviation when you're taking a sample. Okay. However, if you ask everybody, like they did in the presidential election, That's the standard deviation of the entire population. And so they're different standard deviations. This is if you know everyone, and this is if you take a sample. Again, so when we do these on the calculator, you're going to see some examples where there's a regular standard deviation and then a standard deviation p for the population, meaning do you know everyone in the population? Because if you do, use the one with the p. If you don't, use the other one because you're going to get a different answer. And again, you have less certainty here. I don't want to go into the math behind it, but essentially you subtract one somewhere when you do the calculation. And I'll leave that for your stats teacher to talk about, or for everyone in class to discuss this. Or you can watch a video on it on YouTube. I'm sure someone explains it well. But that's the difference between if we know the entire population versus just a sample. So what that means is when we go over to here, I have all this data, right? Well, it turns out that if I really want to get the standard deviation, I don't need to do all this, and I don't need to do all this. All I need to do is say standard deviation, or I could do standard deviation population, and I want you to see the difference. Okay, so here I'm just going to go, my formula is going to say equal standard deviation. You'll see STDEV, and I'm saying, hey, I want to know what the standard deviation is for all of this data. And it spits out 67.57. However, here's the thing. These are all the pennies that were thrown by this group, right? If I only knew half of these and I wanted to guess what the other half were like, I would use this standard deviation. However, I know that this is all of them, so I don't want to use the standard deviation. This is not the correct standard deviation. I want to use the population standard deviation. So you can see ST, do you see the STDEV period dot P? That's the one I want to use. That means, hey, I know this data is everyone. And you can see, uh-oh, I used the wrong one there. Sorry, let me fix that. Okay. And you can see we get the same standard deviation of 66.7 that we calculated in the last, the last time we did it with all the different rows and stuff. This is obviously a lot faster, but you'll notice when we have a sample, our standard deviation is bigger because we have less assurance. If we know everyone, we have more assurance, so our standard deviation is smaller. So if we kind of go back over here and think about what that means, here's the mean, right? Here's the mean. If we have a sample, in this example, the standard deviation was like, was it 67 or something like that? 67.5 versus 66.7. 67.5 versus 66.7. Okay, so once we had the mean, we were saying we wouldn't be surprised if we added 67.5 in this direction, or if we subtracted 67.5 in this direction. Whereas when we had the population, we have a little bit more assurity of what's going on. So now we're only jumping by 66.7 or by 66.7. So we get a tighter, narrower window. Not by much in this example, but obviously the math can change depending on the problem. Anyway, to keep going here, let's see if we want to get the standard deviation of this data. So I can go stat. If you guys remember, this goes back to the sugar W and the sugar P problem, right? So let's just show you how to get the standard deviation of this data. I'm going to go stat, calc, one variable stats. I'm just doing L1 first. I'll do L1 second. I'm going to calculate. This right here is the standard deviation. This is the sample standard deviation, and this is the population deviation. So the question is, when we looked at those sugars, were they all the sugars? If they were all the sugars, this would be the standard deviation we want to use. If it was, if those were just some of the sugars out of all the sugars, then we would want to use this one. By the way, in this class for right now, we're using the population. So we're going to use the population standard deviation and not the sample deviation. All right, so again, just to go through that, what if I wanted to do L2? I'm going to go second L2. I'll calculate. you'll notice that I have the sample standard deviation, the population standard deviation. By the way, I hope you guys are watching these videos because this has not yet come up. But hey, look, there's our minimum, there's our quartile 1, there's our median, there's our quartile 3, there's our maximum. If I subtract that, I'll get the interquartile range between Q1 and Q3. If I subtract here, I'll get the range between 70 and 60. So there's a lot of information when you run that one variable stats that we might not necessarily be aware of. N means number of 19. That means there's 19 pieces of data. That's what that means. So again, hopefully you guys are watching these and getting something out of them. All right. So how do we do this in Desmos then? Desmos is a little bit funkier. We already have this data here. So what we could do is under functions, under stats, you could be trig, stats, whatever, but under stats you'll see standard deviation population. Again, it's kind of on us. We can pick whichever one we want. But when I hit standard deviation population, you can see it sort of jumps over here and it wants to use this data. So I could just type all these numbers in again, but I'm super lazy. So I kind of think like, you know, it might make more sense. Why don't I go over here? Why don't I rename this thing standard deviation population, right? It does this automatically for me, and now there's my standard deviation of the population. Again, if I go here, I'm just going to erase this part of it, and it's going to have standard deviation of the population. And again, we still get that 10.8, we still get that 18.87, which we had already calculated from earlier. But it's just a way to get standard deviation. Now, if you didn't already have that list in, so let's pretend we didn't already have all these lists in, what it would look like is you would say, hey, I want to know what the standard deviation is, and then you would just have to type the list of numbers with commas between them, and that would give you what you needed. So that's the standard deviation of those numbers. If I take rid of the P, you'll see this 4.08 jump up a little bit because now I have less confidence because I'm looking at a sample, not the entire population. All right, so I hope we're doing okay with all that. The last thing I wanted to look at was the math notes. So these math notes are only about spread, right? So we talked about like the measures of central tendency, like the mean and the median and all that good stuff. We're only talking about spread right now. The interquartile range is Q3 minus Q1, and you use this with median. And again, you can always use median. So this is always a go. You can always use interquartile range. Standard deviation is based on mean. Again, you do not always use mean. So you're only going to use mean and standard deviation if you have a normal distribution. Again, the mean absolute deviation we really aren't going to use anymore, sorry. And the range. The range is always calculated. You're always going to subtract the smallest from the biggest for the most part, but they just want to point out it's not super meaningful. You know, again, to go back to the problem example I used a while ago about having, you know, $15 to $20 in our pocket and Bill Gates walks in with $5 million. Well, if our classroom looks like this, between how much money you have in your wallet, you'd see your range is 5 billion. And you'd be like, wow, that's quite a range. It's not really meaningful. Although once you get rid of this guy, now our range jumps way down to 15. So the problem is those extreme values can really screw up the range. So you can use the range. You just want to be real careful with it. I hope all this makes sense. Again, feel free to reach out. This chapter jumped around a lot going from, you know, different kinds of software. So I felt like there was a lot going on. I hope it made sense, but if it didn't, again, feel free to reach out and we can discuss it and go from there. Have a good one.